Today we are going to learn about feature scaling, normalization versus standardization. You will understand the differences, applications, and implementation of these scaling techniques to enhance machine learning model performance. Welcome to our video on feature scaling, normalization versus standardization. In the world of machine learning, feature scaling is a crucial pre-processing step that can significantly impact the performance of your models. Scaling techniques, like normalization and standardization, adjust the range of your data, ensuring that features contribute equally to the model's learning process. In this video, we'll provide you with an in-depth understanding of these techniques, their applications, and guide you through their implementation in Python, empowering you to make informed decisions in your machine learning projects. Feature scaling is vital in machine learning because many algorithms are sensitive to the relative scales of input features. For instance, distance-based algorithms like k-nearest neighbors and clustering algorithms such as k-means rely on calculating distances between data points. If one feature has a wide range of values, it could disproportionately affect the computed distances, leading to biased results. Similarly, gradient-based algorithms, including neural networks, benefit from scaled data as it helps in faster convergence by ensuring a more stable gradient descent. Without feature scaling, models might struggle to learn effectively, leading to suboptimal performance. This block will delve into these aspects, providing a foundational understanding of why feature scaling is indispensable in machine learning.
Normalization, also known as min-max scaling, is a technique used to adjust the range of data features to fall within a specific interval, typically 0, 1. This process ensures that all features contribute equally to the model's learning process, preventing features with larger scales from disproportionately influencing the model's predictions. Normalization is particularly useful when the model does not assume any distribution of the data, or when using algorithms that rely on distances or gradients. While normalization is advantageous for preserving the relationships between data points, it is sensitive to outliers, which can skew the results. The formula for normalization is x, min, max, min, where x is the feature value, and min and max are the minimum and maximum values of the feature, respectively.
Standardization, also referred to as z-score normalization, is another popular feature scaling technique that transforms data so that it has a mean of 0 and a standard deviation of 1. This approach is beneficial when the data follows a Gaussian distribution. Standardization is particularly useful for algorithms that assume a normally distributed dataset, such as linear regression and logistic regression. By standardizing, we can compare features that have different units and scales on the same footing. The formula for standardization is x, mean. Standard deviation, where x is the feature value, mean is the average of the feature, and standard deviation is a measure of the feature's variability. This technique helps in stabilizing the variance and reducing the impact of outliers.
To implement normalization in Python, we begin by importing essential libraries such as NumPy and pandas for data manipulation, and matplotlib for visualization. First, load your data using pandas to understand its structure and identify features that require scaling. Next, apply min-max scaling using the min-max scaler from the scikit-learn library. This scaler transforms each feature individually to fall within the range of 0, 1. After applying normalization, visualize your data to ensure the scaling has been correctly applied and no outliers are affecting the results. Practical tips include handling missing values and ensuring that the same scaling is applied to both training and testing datasets to maintain consistency. To apply standardization in Python, start by setting up your environment with necessary libraries such as NumPy, pandas, and scikit-learn. Load your dataset and examine its features to determine which ones need standardization. Use the standard scaler from scikit-learn, which standardizes features by removing the mean and scaling to unit variance. This process is crucial for ensuring that each feature contributes equally to model training. After scaling, visualize the data to confirm that each feature has a mean of 0 and a standard deviation of 1. It is essential to apply the same standardization parameters to both training and test datasets to avoid data leakage and ensure model reliability. Feature scaling can dramatically affect the performance of various machine learning algorithms. For instance, k-nearest neighbors, KNN, relies heavily on distance calculations, making normalization or standardization crucial for accurate predictions. Support vector machines, SVM, which also depend on distances, can benefit significantly from scaled data, especially when using kernels. Neural networks, on the other hand, achieve faster convergence and better performance when input features are standardized. By applying both normalization and standardization to these algorithms, you can observe differences in performance metrics like accuracy, precision, and recall. Understanding these impacts helps in choosing the right scaling technique tailored to your algorithm's needs.
Choosing the appropriate scaling method for your project involves several considerations. First, analyze the algorithm you plan to use. Distance-based models often benefit from normalization, while algorithms assuming normal distribution might require standardization. Also, examine your data's distribution. If it is skewed or has outliers, standardization could be more effective. Additionally, consider the scale and units of your features, and how they relate to the model's requirements. Project-specific guidelines, such as computational efficiency, model interpretability, and domain knowledge, also play a crucial role in determining the scaling method. By weighing these factors, you can make an informed decision that optimizes your model's performance. While feature scaling is an essential step, it can present challenges if not implemented correctly. One common pitfall is data leakage, which occurs when scaling parameters are derived from the entire dataset, including the test set, leading to overfitting. To avoid this, always fit your scaler on the training data and apply it to both training and test datasets separately. Handling outliers is another challenge. They can skew normalization results, so consider using robust scaling techniques if outliers are present. Ensuring consistent scaling application across different datasets is crucial for model reliability. After scaling, verify the results by checking feature ranges and distributions to confirm that the scaling process has been correctly applied. Adjust your scaling strategies based on these verifications to optimize model performance.
In conclusion, feature scaling is a crucial preprocessing step that significantly influences the performance of machine learning models. By understanding and applying normalization and standardization, you can enhance your model's accuracy and efficiency. We've explored how these techniques impact different algorithms and provided guidelines for choosing the right method for your project. Remember, consistent practice and careful consideration of your project's specific needs will empower you to make informed scaling decisions. Thank you for joining us on this journey to mastering feature scaling, and we encourage you to apply these techniques in your future machine learning endeavors.